To find the CLNS adjacency state on Cisco IOS, as the slide shows, we use the command show CLNS neighbor. And that shows where the router has found adjacencies talking the CLNS protocol. To find the ISIS adjacency state, in other words, we have exchanged IPv4 prefixes, do show ISIS neighbor. And that shows the IP address of the neighboring router and various other information, including the hold time, which is the time the router waits before it declares the neighbor has vanished. Starting ISIS on Cisco routers is very simply a case of doing router ISIS and then specifying an identifier. The identifier could be the operator's AS number or some other word to indicate the process ID. Most operators prefer to insert a process ID. That same process ID has to be used on all interfaces that are participating in ISIS on that router, and it avoids configuration accidents and errors happening within the network. The process ID is not passed between routers in the autonomous system. It is unique just to the router and gives the possibility of running multiple instances of ISIS on one router if desired. IP routing protocols have a router ID to uniquely identify the router. Well, ISIS is not an IP-based routing protocol, so it doesn't use the router ID in the same way as OSPF and other protocols do. Instead, it has a network entity title, NET, which can be from 64 to 160 bits long. The typical scheme used by many operators today is as shown on the slide. The first 8 bits, we usually pick a number and is usually 49. Doesn't have to be, but that seems to be widely used. The next 16 bits is the area. Typically 0001 is used. The next 48 bits are the router loopback address, where we take the IP address of the router and code it into 48 bits. And the final 8 bits are 0. So for example, we could have an NSAP of 49.0001.1921.6800.1001.00. That is generated from the IP address used for the loopback. The IP address is 192.168.1.1. We insert the leading zeros in that IP address, move the dots across, and we get the 1921.6800.1001 to form the 48 bits of the NSAP address. This way, we can make sure we have a unique NSAP address for every single router on the network, because the loopback address has to be unique on every single router in the network as well. Other operators use this alternative scheme. This one is a little simpler, where the first 8 bits are usually picking a number. Next 16 bits are the area, which we leave at 0001. The next 16 bits would be a point of presence identifier. The next 16 bits would be a router identifier, and the final 8 bits would be 0. Many operators who are deploying IPv6 use a similar type of POP and router identifier scheme for doing the v6 addressing across their backbone. So this NSAP addressing plan maps very nicely onto deployed v6 addressing plans. So in the example I've shown, the NSAP address would be 49.0001.0009.003, which represents router number 3 in point of presence number 9.